So I don't know if John will literally follow us today, but he wrote that he may be late. But he plans to be here physically next week. So, did you got the printouts? So there should be two. One general thing and another presentation by Aaron. So we do have a couple of announcements. So paper by Aaron got to the stage where it can be downloaded completely. It took like a couple of months, and it didn't go the page and volume numbers. And paper by Yvonne accepted like 3-4 months ago. Finally got the volume and page number, so people can start citing it. There will be a local conference on October 12th and 13th. It is very incompetitive. It is not the strongest record in your city, but why don't we try to brag with our records or projects in development? So please compose abstracts or just slightly modified abstracts from your previous conference. And you can send it to me briefly just to glance through. Basically, I don't care what you write there. And then forward it to Dr. Parent, father and mother, that's his last name, Alex Parent. And I did forward his email to all of you. So it will be like poster session, but there will be 1 or 2 international speakers, therefore it's called international conference. But for us it is more like a little kick to update whatever we do and show posters. So just do something, do not take it super seriously. Fatima, you are welcome to show there whatever you like, your old work or probably. So I don't think there will be any paid registration, you just come and show the poster. But you need to send an abstract in order to get a spot on the wall. So next week, hopefully John will present on his polyoxytitanate paper. Although as closer he gets to defense, the more independent he becomes, which is nature. Maybe he will decide to present something else, but hopefully. And then I've got some positive answers to help me with literature review. So there will be a little of literature review next week. We'll discuss it. And since there are changes in travel plans, Aaron may want to present his first draft of proposal next time. Like, it will be a couple of pages. He will maybe tell introductory words, and then we will sit and kind of grade it. For Dane, who also has committed to write a proposal, the deadline is not as soon, but it will be same thing for you too. You'll compose something and you will go over. From what I observe, we may want to refresh our skills in some basic protocols of computational chemistry, and I wonder what if we plan on devoting one of the meetings to refresher. So we'll split major operations that we do between whoever comes and do like 10 minutes presentations. Like how to prepare files, make sure the job doesn't get cancelled, that all files are in place, how to post-process, how to prepare and plot density of states, what are absorption spectra and how to compute them, maybe even how the code of absorption spectra is constructed, and why it doesn't accept too large files. and maybe some updates on non-adiabatic couplings and same optical absorption code for spin polarized and spin orbit coupled cases. So, something like this. Liberal, simple program, but then we will feel comfortable when going on these projects. Any critique or okay? So let's invite Dane to give a brief update on his research, and then Aaron will talk a little longer.
All right, oh, just a little update from last week. This is a screenshot after geometry optimization. I rebuilt the cell and re-optimized to make sure that it didn't blow up. I did watch the movie, but I couldn't remember how to process it into a file that I could put on a PowerPoint.
Why don't you ask us how to do it?
I keep getting that, like after you go into VMD and then you go to Movie Maker, when you click the button to like make the actual movie, it gets to the last step and then it says need source file or something. So I remember it was a simple fix. It was just something that I ended up downloading it and putting it in my.
Let's think. Just write email to all of us.
Yeah.
Someone will answer, but there is a pop-up menu when you create Movie Maker, and it needs information about format.
Yeah.
The simplest format is screen capture, because other formats can be not available on a specific computer.
Okay.
Then there are options like, do you do trajectory or just rotate the model? So you need to make sure that it is trajectory. Then output file, which should be some standard MPG4.
Yeah.
And then you need to identify to give the path and name for your output file.
Yeah, I think it's the path. That's where.
If you do not, if you keep it mute by default, it will find some garbage place on your computer that you will never find.
Okay.
So you need to explicitly write which directory and which file name. Otherwise, it will be like temporary file somewhere in the garbage basket named unnamed.
Okay. All right.
Okay, please keep going.
Yep. So success. It didn't blow up.
What do you plan to measure interatomic distances and report them on the slide next time?
Yes, I can do that.
Oh, how nice.
All right, and then this was, I did the same thing as last week where I just took out the platinum atoms and then ran it in geometry optimization. Now I see that my dinitrogen tetroxide molecules appear that they're too far away now. So that needs to, I should probably fix that. I'm gonna plot electron densities on it and see if they are bonded or not, but it just, none of them look like they're bonded, so.
Okay, and as time goes by, please plan on plotting so-called density of states. Just task around, it's something simple, but it will be a good complementary information to whatever you do.
Okay.
As a reference point, you need a simulation cell with cluster only. Right now you remove the cluster and kept molecules, but you made to remove molecules and keep cluster.
Okay.
It's not a big science. There is no reaction without reactant.
Mm-hmm.
But to see which charge density and which electronic states does it contribute.
Okay, so have all three?
Yep.
Okay. Alright. And then just progress report of ongoing jobs. I got heating jobs submitted, so working on collecting molecular dynamics from those two previously talked about. Pulling together an abstract for the conference coming up here. I'm also reading through Victor Batiste's paper. I actually haven't opened it yet, haven't had a chance to read through it, but I'll be editing it a little bit, and then be writing an introduction for Dr. Han on one of his research papers on monomethylhydrazine and nitrogen dioxide, correct?
So how far is your GRFP proposal? You may want to start planning it right now.
Okay.
Because like my handwriting pace is a page per hour. Therefore, I can write a proposal in 2 hours, which is wrong. It will be.
Right.
You need to make like a plan, discuss it.
Okay.
So do not push it to the last night before deadline. And they need a lot of garbage information, like your list of courses or reference letters, which some reviewers do not read them, but you need them. So you need to contact people and make sure that they do it. Even people who think highly of your scientific skills, they will not behave like puppets in 5 seconds later.
Okay.
So you need to
Jump on it. Sounds good. Alright, yep.
Any questions to Dane about his impressive research progress? Any suggestions?
Were those models fully optimized before you had submitted heating jobs?
Yes. I had in my in the debug file, I had it for 30 minutes, and I had to run the one with platinum, I think, 3 times before it stopped, before the 30-minute mark.
So
Does heating generally take longer than optimization, or no?
no, and you can make shorter heating. There are some tricks. The amount of numerical resources scales very non-linearly with size of system. So in the best case, it's like a cube of number of atoms.
Mm-hmm.
So there is no wonder that 100 atoms will be like if you double the number of atoms, it will be 8 times longer at least.
Right.
Typically, it's much less favorable scaling. So it's not a big surprise that this relatively small model is fully optimized in short.
Especially on Nursery.
Okay. Yes.
I bring up that email that you forwarded to me about running the debug file.
It's fine.
That's
They
okay.
do not mind. They
Okay.
give us better opportunity that we work more efficiently. Debug allows for 30 minutes. They develop some new queues that allows for 4 hours,
Okay.
and they invite us to learn how to use it.
Gotcha. Okay.
Okay, let's thank Dane. It promises to be a not very long video. So your file is somewhere on the
Desktop, probably.
Yep.
Looks like it's on the screen.
Good.
So I'm going to be talking to everyone about doing some geometry optimization for the perovskite quantum dots models that I'm working on, and then some observables that I've collected from these perovskite quantum dots as well. So first, well, you can look at the perovskite quantum dots that models we're going to be looking at. So for the cesium lead bromide based quantum dots, so on the inside of the dots is bromide and leads and cesiums. We have 4 different systems we're looking at, which can kind of be broken into 2 parts. So on the left, we have a small quantum dot with ligands that I forgot to put the picture on. So and that one's undoped, and the one below it is basically the same model, but in the very center of the core, there's it's doped with a magnesium atom. And then the same deal on the right, these are just bigger quantum dots without ligands. And then the top one is the undoped model, and the bottom one is the doped model, where if you can kind of see in the very middle, there's a little purple atom, and that's the doped magnesium in the core. And then there's also one other model that we're looking at. So it's a iodine-based quantum dot, where it's iodines and leads on the inside, and then we have ligands on the outside, terminating the surface. And so usually we've been having a little bit bigger crowd, so I figured we could put in a little motivation for while we're looking at these.
Motivation is good all the time, and you are on the tape recorder, so you can put it for bigger audience anytime.
Okay, so I arranged these going from left to right. So to begin with, colloidal perovskite quantum dots show tunable emission across the visible spectrum by just changing the halide solution. So you can see all these pretty vials of each composition photoluminescing. So on the right, those are cesium lead iodine based perovskites, which emit in the red region. And in the middle, you get cesium lead bromide, which emit in the green. And then cesium lead chloride, they emit in the blue. And then if you mix them, you can get colors in between. So that's how you can get the full color spectrum, just from not even changing the size of the dot, just by changing the chemical composition. So it's pretty handy that way, so you don't have to have total control over size. But one issue that's arisen with these perovskite quantum dots is with the cesium lead iodines. So it turns out, just due to the iodines being pretty bulky, that it doesn't like fitting into the cell very well, and it wants to expand. So you can see in the middle picture, it's when they're synthesized, they're in basically a cubic orthorhombic type of cell where all the sides are even. But after time, it wants to expand and go out, and it goes into a different crystal structure, which doesn't give the nice red photoluminescence. And these ones have a very high band gap, like 3 eV. So it's tough to get stable emission from these red quantum dots.
Aaron? So what breaks them? Heat or light? Is it like thermal degradation, photo degradation? If you freeze it to liquid helium, will they be stable and emitted, right? Or it will corrupt them more?
I think it's heat. It's phase transition from the 3D orthorhombic to 1D orthorhombic is around 320 degrees Kelvin. So it's heat-induced phase transition. So at lower temperatures, it would stay in the metastable.
But they are photostable. So if there is no heat, just exciting and letting it emit again and again will not damage.
It won't change the crystal structure. There's opportunity for the halides to move around. So there's degradation that way, but it doesn't change phase necessarily. So this is a heat-induced. There is light-induced phase transitions too, but which is also a problem. But the biggest one, not allowing for stable luminescence, is the heat-induced phase transition. So what people in the research community have done has said, well, cesium lead bromide is a pretty stable quantum dot. And then, I don't know, what's the best way to put it? So in the material science community, like if you're trying to get something to emit with the red color, usually one idea is to dope it with magnesium, which is seen on the right. So
I have a question. So you said the quantum dot is doped with magnesium, but I think this is manganese
or manganese. Yeah, my brain uses them as synonyms, so it's manganese. One of the
What will be the
metals.
color if you dope it with magnesium?
It probably wouldn't have a color. I don't know if it would be stable.
Does magnesium has d orbitals?
Magnesium's below lead, right? Or it's a couple rows. Or am I thinking something else?
No, magnesium is
Oh,
the
here's
second
the
group, right?
certified chemist.
I thought magnesium is the second group. carefully. I carry my handy dandy periodic table.
So it should be second row and
Yeah, magnesium's the second group, so it's got no D
Mm.
orbitals. Well, not in its outer shell, right?
Right.
That's,
Right, so good catch. It's manganese, not magnesium. So then, yeah. So the paper that I cited here, they didn't really dope it with manganese. They basically substituted half the leads, and they're able to get a deep red color. And you can kind of see in their diagram, they say that they can get the red color due to interactions between the manganese ions, which isn't available just for light doping. So without the doping, you get a yellow emission. But by over substituting, you can get the redder emission. So that's kind of one of the research pathways that people have looked into to get red emitting perovskite quantum dots that are stable.
so if you have manganese atom or manganese ion in a vacuum, will it emit yellow or red?
Just one. It should be yellow. Well, based on just the research that I've done
So
from this research paper.
once again, manganese 2 plus, same ion as in this doping, but placed in a vacuum. Which color will it emit?
It'd be yellow, wouldn't it?
Would you like to correct me?
what are you asking? How come it's not red? What's the question? Do they make quantum dots of fluorine at all?
They may be fluorinated, like on the surface, but not with like the interior.
So which row manganese is at?
4.
Or 4.
4. And how many d electrons does it have?
Well, I mean,
If
it would have a full
it is
shell. It would have all.
no, if you have removed 2 electrons.
Well, it has F electrons. It's in the F block. It's a transition metal,
Yes.
so it would be like if you removed its electrons, it would be in the S block then, right?
So how many electrons is on the d orbital in neutral?
All 6. What?
And if you
Because the d orbital is over here, right? So it would have a full shell of d orbitals before it
no,
started.
yellow is d orbitals. Yellow is d orbitals.
Oh, these are
Oh, yeah.
p. These are p.
Yes.
Oh, yeah.
Do not make me to
Sorry.
to
So
develop any suspicion.
it would have 5. Sorry,
Okay.
I'm
So-
here.
And in front it will be some. What is the noble gas in front of it?
Argon.
Right.
Mm-hmm.
So in vacuum. 1, 2, 3, 4, 5.
2s.
Huh?
And 2s. Do you need to include
2s
those?
somewhere.
Doesn't matter.
We will convert. And then they will. Maybe become unpaired or paired, but 5d orbitals. So where will be the transitions and of which color?
If it was excited, it would go.
But it will be very S and P and D of this noble gas. They are much higher above or much lower below.
So it'd be UV.
Yeah, it will be UV. And what happens in the crystal?
You get splitting from basically the Stark effect, right?
Mm-hmm. So can you draw something and explain a little more? Maybe erase it and draw it from scratch.
Yeah, so I guess the point that we're getting at here, so if it was just the ion in a vacuum, like all these levels, these D levels would be pretty much similar in energy, and like before there'd be UV above and below, so large transitions from like maybe 3 or 4 eV. But then if you put it into like a crystal lattice where it's ordered, so it's, say if we had Mn in the middle, and then here would be, in the perovskite it'd be bromides on each side. So then, so now it's not by itself, it's in like an external electric field from the p orbitals of the bromides. So then that electric field is going to shift these d orbitals up and down in some fashion I'm not familiar.
In which pattern? Can you sketch the pattern?
Just from memory, I think it's 3 below, 2 above.
Okay.
I couldn't tell you whether they're z squared or x squared minus y squared.
That's fine. So does the amount of splitting from up to down depend on the type of ligand you have around? Will it be the same for bromine versus chlorine versus iodine?
Based on halides, I don't think so. Wouldn't they give all the same splitting? Because they have the same valence electrons,
They have the same charge,
same charge.
but they have different ionic radius. They will be on different distance. And
so
then it will experience slightly different splitting.
So
We assume that the one with the larger radius would have more splitting.
Or less, because they are far and coulombic law. If like inversely proportional to the charge. Do you remember in class Levi was doing presentation? If something is going wrong with how you explain it, it means Levi did a bad job in presenting it in class.
I remember him presenting it. I don't remember.
Okay, so it's crystal field splitting or ligand field splitting, which considered as extremely advanced topic for physics education, but very simple background alphabet in chemistry education. I have no doubts that Dane knows it with closed eyes in the middle of the night. So it's like second year in organic chemistry, right?
So then, yeah, then in this arrangement, ideally, this gap would be somewhere like 1.5 EV, 1.6.
Okay.
So then that's how you can get the red emission.
So the splitting is what affects the color? Is that what my understanding is? So the more splitting, the redder it is, or less splitting, the redder it is?
Second
There you
was
go.
correct.
Is that less?
If there's less splitting, they'll be closer together. So you need less energy to bump it up.
Okay.
Because like before, if it was just in vacuum, you need a lot, which would be like UV.
Okay, sorry for interrupting you. Keep going.
No, that was helpful. So then, yeah, that's just kind of a 5-minute motivation for why we're looking at these crystals. Then specifically, eventually we're going to be looking for maximizing the quantum yield for each of these.
How do you define quantum yield?
So, number of electrons in. So you count those divided by electrons that emit from the band gap that you want, or from the states from the homoluminal gap. That may not be the broadest definition, but that's how I'm thinking of it at the moment.
Everyone buys it?
Say it again, sorry.
So like, so say you have, I don't know, some sort of material. You shine one photon in, and then, so say you put like 10 in. Ideally, you would like to get photoluminescence coming out, which matches some ratio. So this would be
Or
so if this was V1, this is going to be U2, which is going to be less in energy. And ideally,
But you can't just number of quanta. You want to absorb 10 quanta and emit 10 quanta.
right?
But sometimes it is not happening because like absorbs 10 and emit 9. 1 quanta went into heat. So this ratio of emitted to emitted plus heated. Like if 9 went to emission and 1 converted into heat, then efficiency will be how many percent?
90.
Yeah.
Okay. Yeah. I'm convinced.
So it can be any light that comes out, not necessarily
Emit
like which
divided by emit plus heat.
plus heat.
Or
Right.
emit divided by absorbed.
No. In philosophical sense, correct, but
Chemically not.
no. Chemically also, but you want to add more detailed mechanistic analysis of what is happening after photoexcitation. It can be split onto more than 2 reaction pathways, and you better deal with efficiencies of what is happening after excitation, because I don't know, tradition. But formally, it's correct. Emitted to absorbed works too.
Okay, so then these are just a couple of general expectations to keep in mind when I'm going through all these models and looking at data. So the figure on the left is from a paper by John Parkhill, who does some work on, or has done some work on perovskite quantum dots. And this is a density of states comparing the density, or applied density states for different sizes of quantum dots.
So
and bulk.
what is CHS?
In the paper they called it confined whole state.
Okay.
So basically what we found is for the bulk system, you get a pretty continuous change in the density states in the conduction band and the valence band.
Mm-hmm.
But then as you decrease the size of your quantum dot, you start to see a little discontinuity. You see a little bump in the valence band. And they claim that this is intrinsic to the perovskite quantum dot structure. Because they did this with
Sorry, I want to. I see this touch screen, but it doesn't have the. Oh, it does. It does have annotation. I don't know how to formulate a question. Let me ask it like, would you agree this delta and this delta are the same?
so by changing the confinement length, you change
So if we consider your dot as particle in the box, the confinement increases the splitting between first and second state. And if you count energy of electrons here, there is a confinement of electrons, but then you count energy of confined electrons to the right, and then those features will be first, second, third states as same as here.
Wait, so it's not backwards? But just
It will be same forwards for electrons, but for holes, the higher excitation energy, the deeper is the hole in the valence band. Energy progressions goes opposite. If you increase energy of excitation, electrons are excited higher and higher, into conduction band, and holes are getting excited lower and lower into valence band. So higher excitations means you have big offset from the gap to both sides. And quantization for holes, lowest quantum state is edge of the valence band, and higher harmonics are deeper in the valence band.
That makes sense. I guess I always considered it, well, I always thought from the electron perspective, so the lowest energy would be, I guess, holes. You just have to flip everything.
Okay.
That makes sense.
Any objections or questions to Aaron? When you will continue whatever you do, just a second, So what you are doing now, it is not yet a true research. It's more like education. But Fatima is doing linear chain of silicons and looking for electronic structure as function of the length. Right now, this 2, 3, 4 is too few. But if you do 10, and then you draw not the HOMO and LUMO orbital, but you draw HOMO, HOMO -1, HOMO -2, several orbitals. It is expected that you will see the same progression as Aaron is showing with yellow things. So there will be quantization, and you should be able to see same trends in density of states as an education, in order to apply the same ideas later for larger systems. So, and no one is objecting the concept of particle in the box, right? Good. Okay, let's keep going.
Well, I guess these dots are smaller than usually what's looked at experimentally. So I was thinking usually, well, for the particles I've made anyway, I haven't seen any drastic quantization effects, but these are smaller.
Even if you are extremely skilled experimentalist, there are objective difficulties to get monoids per sample. So this simulation is for one dot, but as soon as you hit it, if you have a sample of inhomogeneously broadened dots, even if they are of the same size, they are a different phase of vibrations, and the quantization size here is comparable with thermal fluctuations. So for a single dot you may not see it, and it's okay. To see the structure, one may want to set up single molecule spectroscopy. When you spread your solution very low concentration on a thin sample, so that dots are offset from each other on a macroscopic, like a millimeter or like noticeable fraction of millimeter, and then you in one direction you excite it, and then you look on a microscope, and you see several dots flashing, but you can identify only one. And then you point microscope and take spectrum, and then you will see features of one thing. You will please correct me. I never been in the.
All you said is correct.
Okay, thank you. It is. I never touched apparatus. It's just from reading papers. General idea.
That's interesting. Well, I think they figured experimentally they found this effect first because through a Stark shift, or not Stark shift, but a Stokes shift. They found a size-dependent Stokes shift, and they use this as their explanation.
Quantum confinement for quantum dots. Not only quantum dots, even thin films. It is declared in many different systems, but we cannot claim that we are the first who see quantization of states in perovskite quantum dots, because it was rediscovered in silicon quantum dots, cat-selenium quantum dots, so it's any nanostructure. And not only dots, it's like films, nanorods, it's general common knowledge. It's like a central idea of nanotechnology at all.
So
it's just the declaration of this feature of any nanostructure for this type of system.
So for any sort of quantum dot system you're looking at, you'd expect to see some sort of, I was thinking Stokes shift, just based on quantization.
It is not Stokes. No. Stokes, well, you can tell it is. No. It's
because in the paper they claim that this feature here is dark, and that the absorption actually happens from this peak here up to here.
which one can you point?
So from not the CHS state, they claim that absorption happens from the valence band edge state here and goes to the conduction band edge state, and then photoluminescence happens to the defined hole state. That's what the paper claims anyway.
Well, I didn't read this paper, and I can be very wrong in misinterpreting, but there is a quantization due to confinement, quantum confinement, for this progression, and there are trapped states due to defects on the surface. Hi, John.
Hey.
Please tell something to us.
How are you?
Doing good, thanks.
Perfect.
Do you see slides by Aaron?
Yes, I do.
Okay. So we have a intellectual challenge. Do you see annotations that we do here on the screen?
Yes.
So you see this notation of CHS and VBES.
Okay.
So we have a question if the CHS originates from quantum confinement or it is just a trap state.
Okay.
So your input right now or later is appreciated.
Let me see. I'm gonna look through the PDF with the previous slides on them, and then in a couple minutes, hopefully, I have a comment.
Okay. Yeah. Thank you.
Okay, so I guess we'll move on to the other half of the slide. So basically, this is just saying that we should expect our orbitals to be inside the quantum dot, not on the outside of the surface. It should be delocalized over these, ideally with the HOMO on the iodides or the bromides, and then the LUMO on the leads, and some sort of hybridization between them. So here I'll just outline a computational experiment I've been running to optimize the one in the quantum dots over the last couple of days. So the quantum dot I'm looking at is the large quantum dot with no ligands, no dopant. So since there's no ligands, or I guess I don't really have to worry about the dopant, but since I'm not dealing with ligands, I don't have to worry about contracting those bonds, so they're not going to spring out. So the idea that Dimitri proposed is to just squeeze the cell size a little bit, because that's effectively going to change the bond lengths of all the bonds within the quantum dot, and then just plot that, and you should see some sort of parabola to be able to find the minimum, just based on changing the bond lengths of the squeezing parameters.
Before we go to this really interesting and important subject, I would like to, on your behalf, ask Fatima. Well, first I will ask you, and then I will ask her. Does the geometry of surface atoms continue the symmetry of bulk? If you keep the pattern of the interatomic distances, would you agree that, or disagree that atoms on a surface are on the same interatomic distance as inside the dot?
They may be there's roughly the same distance, but they're at different angles.
Okay, so geometry
Is different, yeah. So
on surface is different than in the bulk.
So you think of it as like the inside cube being a core, and the perovskite on the outside kind of being like a shell that rearranges around the core.
Okay. Now, we have a surface scientist, certified surface scientist here. Can you explain us what is surface reconstruction in your own words?
So if we have a crystal and we cut a different plane, so for surface reconstruction we need to apply current through the sample. Normally we do research, and then the atoms reorganized on the surface and got different structure than the.
Okay. So
So they're kind of optimized with heat.
yes. Annealing.
Yeah.
So you, it's not melting. You just heat and then freeze. A little below melting, but it changes surface arrangement of atoms. What is our benefit? What do we get out of it? Even if we are very narrow-minded computational chemists.
More consistent results, maybe, throughout.
Energy is minimum.
Huh?
Energy will minimize.
Yeah, this is correct, but what about traps of electrons and holes? Surface states in the gap. So I do not know how to put it in a context of nicely sounding or nicely looking, but if you take bulk structure of any semiconductor crystal, like if you target the semiconductor quantum dots or other nanostructures, even surfaces, you cut, and then there are atoms that are missing neighbors, which means they have lone electron pairs, and these lone electron pairs will develop states inside the gap. So even if the material is known experimentally to be semiconductor or insulator, this big amount of lone electron pairs with low energy inside the gap, they will predict that the model is a metal, which is wrong. And then there is a contradiction between simulation and experiment. So in order to avoid these trap states, there are two ways. One is to cap each orphan atom with the ligand, which is correct experimentally. So Aaron may correct, and one day he will present his experimental effort about how to put ligands on quantum dots. But for computation, as you will see from his calculations, ligands are extremely expensive. And we can do it as an artificial computational trick, or we can correlate it to nanostructures in vacuum under annealing conditions. So if you let these orphan atoms that miss neighbors to anneal, they will find each other in such a way so that they compensate their lone electron pairs, form another bonds, and the states will disappear from the gap area. So it is basically what Aaron is doing and demonstrating right now. If you see in the upper right corner the structure, which probably we can enlarge or Okay, next slide or yeah,
A little bigger.
here. You see that inside they are perfectly cubic, but outside they do some curved angles. And this little curving of angles is almost sufficient to remove almost all trap states. So probably Aaron will return to this aspect by his own words in few minutes. Okay?
So like in, I think in another way you can say like in the surface, the atom has dangling bonds, right? So after annealing, they will find
Someone to bind with and get away.
neighbor.
Yes. Yeah. So it is now, thanks to Fatima, we did a collaborative effort to explain what is surface reconstruction. Okay, please continue.
So, yeah, I should just mention for people who don't know, if you look at the postcard, there's a number here that's usually 1, so that means that your cell size is 1 for each of your diagonal elements. So then if you made this 0.9, that's going to reduce your cell by 0.9 or whatever your x, y, and z values are. So if this was like 20, it would decrease it by 5%. Or decrease it by your cell size by 5%. And then if you expanded it, you would be, well, expanding your cell. I call it squeeze parameter since I'm squeezing the system. But anyway, so then I plotted for different values of that parameter. I started with 1 and 0.9, and I realized I'm kind of at the higher ends of my parabola. So then I looked at numbers in between, and you can kind of see the minimum occurs around 0.5 or 0.6 for the squeeze parameter, and those usually correspond to about lengths of about 3 angstroms for the core interior lead bromides of about 3 angstroms. So then from there it's basically just geometry optimization and some computational tricks to try to speed up optimization. So, and then these are just some observables from the system. So you can see that for the HOMO orbitals, there's definitely a trap state on the shell just because it's not reorganized well enough. You can see for the LUMO orbitals, they look pretty good for the most part. You can see in the interior, it's very delocalized throughout the core, mostly on the lead atoms, but there is still a little bit of a trap state on the surface, and ideally we'd like to remove that and have that electron density put on the inside with the perovskite quantum dot. And if you look at both of these images, you can see that the defects happen along the z-axis for both of them, with the positive charge being on the upward z direction, and then the electron or negative charge being on the south end, which I'll mention in a minute. And then that's just the density states of the plots, and you kind of see some of the quantization effects.
Can I interrupt? So before we go to density of states, it is very interesting finding and observation, although it is byproduct. In the final, I hope that in final set of results, Aaron will not have it. But right now, he has hole on one side of the nanostructure and electron on the other side. In which situation this can happen? Or let me simplify the question. I just set it up for my hypothesis. Which direction electric field should be oriented to have this arrangement of charges?
Should be upwards.
Okay,
Yeah, and then positive z.
so the arrangement of anions and cations is not balanced, so that it creates total dipole of the system oriented upwards.
Oh, that's a hypothesis anyway.
Okay, and if you match position of all anions and cations so that they will have the same center of mass, the total dipole will disappear, and the HOMO and LUMO electron hole will be centered in the center of the dot.
Hopefully, or not just migrate.
Okay. So what's about those?
And nothing too much to report. So this is a quantum dot, which will be about three angstroms. I think 2.93 angstroms, and it's showing some quantization effect. Where you can see this peak kind of stands out from the rest of the slides.
So the same question as we discussed before, and maybe John has answered it now. So this feature at the top of the valence band, is it a signature of this surface defect hole, or it appears because of quantization?
I would assume probably a little bit of both, because the upper state is obviously going to be the defect because that's the HOMO. But then I guess I didn't look at the lower orbitals to see if they were on the inside, so it could be a mix of both without having full knowledge of the situation.
Wonder if this one is HOMO, which has this surface feature. And then if we minimize the width parameter for this Gaussian dressing, maybe we will see more fine substructure. Like this one can be quantization. How do you call it? CHS. So, John, what do you think?
I mean, I think that's totally possible. I mean, the dopant states sit very, very closely to the top of the valence band. So yeah, if you would reduce that signal parameter, from whatever you have it set at when you plot it, something down, you might see that it completely separates.
Okay. Yeah. Thank you.
Yeah, just to mention, I tried to compute oscillator strength through the system, but it gave a segmentation fault. And I've been playing with the script, increasing parameters, hoping that one of them will allow it to read the wave card.
So would you like to ask John if he ever faced the same problems?
Oh, while he's here, might as well.
So yes, I have run into issues with segmentation faults in this script. Primarily, they were due to calculating oscillators at various K points. And so the calculations at different energy points require a different number of plane waves than at the gamma point. And I found that when the plane wave is different from what the gamma point is, then it throws a segmentation fault because the loops in the bottom half of the dipole script time out. So I don't know, are these all done at gamma point?
Mm-hmm. And I've tried decreasing the orbital window too, so it's, well, last time I had this error, that fixed it, so it's something else this time that's causing the segmentation fault.
I mean, have you played with any of the cutoff energies within the in-car file, like lowering or raising them to see once what might happen?
Which files?
In the in-car file, you can change the maximum plane wave value. Or,
oh, right. I haven't done it for this system.
Okay. Because I don't know if there's a case where going to some of the higher cutoff values might have an issue. Dr. Kill might have a better idea about that. But those are two issues that I can think of.
Yeah, I can try that one, but I don't know if it's the error with reading the wave car though, because in the oscillator script file, when it reads in or allocates resources to read in the wave car, I increased that by 2 or 3 orders of magnitude, and it still gave the same error. So,
which machine do you run this oscillator strengths? On HPC or on NERSC?
HPC.
So maybe you may want to run oscillator strengths on NERSC too.
Is that in the bin?
Even if it didn't, you can just port .f file and recompile.
Mm-hmm. Yeah, I can give that a go too.
But thanks for identifying the difficulty.
So yeah, we kind of talked about this already a little bit. So possible causes of trap states along the z-axis. So one of them was the internal dipole moment, just due to the cesium atoms not being totally in line throughout the entire structure, creating an internal electric field. And then another idea I had was that my cell sizes for my X, Y, and Z aren't all the same length, and my z-axis is a little bit larger than the other two, so it's getting squeezed less, yeah. So it's getting squeezed less than the other atoms, so that could be a cause why the defects are occurring on the z-axis too. And that was something I was going to change, make them all equal, and see if that changes anything. And then the rest of the sizes are just some preliminary observations of the other systems that I mentioned in the beginning. So here is the same large quantum dot, but doped with manganese on the inside. So you can see for orbital 124, the HOMO is pretty well delocalized within the quantum dot on the bromides. And then we have states lower than the HOMO of the perovskite due to the manganese, which is a good sign, which is what we wanted, because we want the manganese to be on the inside of the gap of the perovskite quantum dot. And then we get the LUMO of the perovskite on the leads pretty well delocalized over the quantum dot as well. But then the one issue with this model is you can tell it's not fully optimized yet, because these are the orbitals, or these green boxed are the orbitals for the manganese. You'd expect there to be about a 1.6, 1.7 EV energy splitting between for 127 and 128 orbitals for the spin up orbitals, but here you can see a 0.2 split, so that means that the manganese hasn't optimized with the bromides on the inside yet to get the crystal field splitting that we want. And same deal for the spin down electrons as well. And then my idea for this one is just to completely optimize the undoped model first. So I get rid of all the surface trap states and then dope it with the manganese, because that would be ideally the quicker way to do it, instead of doing two models at once and dealing with two different problems. So this model is a small quantum dot, so it's just a 3x3 cube or 2x2x2 cube with ligands attached on the outsides, and the ligands are one of them is a carboxylic acid, which is anionic. Those are the ones with oxygens at the end here, and those are over the lead atoms. Then you have anionic ammonium-based ligands, which are over the iodides in these models. So you can see that just from a little bit of optimization, the HOMO orbitals look pretty well delocalized and not any trap states near the surface, although you can see some density on the ligands. The LUMO is the problem with this one, as it's they're spread out over they're localized to different regions of the dot, and ideally you'd like it to be delocalized throughout all of them. And I haven't done as much work with these ones yet because, as Dimitri mentioned earlier, they're computationally heavy and they require a little bit more precision just because of the ligands. So my plan is to work on these ones a little bit more after I get the big quantum dot optimized.
I think we want to submit like long optimization jobs into queue and go to the group up. You can submit like 100 jobs and do nothing.
Yeah, there's that option too.
Even if something bad happens to them, it's John knows about Sergei Tretiak instruction how to go hunting. Can you tell us his suggestions?
carry lots of bullets, shoot at everything, and eventually you'll hit something.
What did he say?
So the connection is not perfect. I'll take fun of repeating this joke. So suppose you're a hunter. You want to bring something home. So there are two ways of hunting. First, you take your rifle, go walk long target, shoot once, and bring or bring not whatever you're hunting. Second one, close eyes with black band, take a machine gun, shoot 1,000 times, then open eyes and see if you got something. So the biggest scientist in my close environment, I don't know if he, he's going towards big scientist on a global scale, Sergei Tretiak, and John was working with him in summer school, tells that it is much more productive in computational chemistry to take the second routine. Just prepare 1,000 jobs, submit if you have to the cluster, and then wait until and then just open eyes and see if any of them brought interesting results. So you shouldn't wait to start the job. You can, if your model is ready, submit the job. 1, 2, 3, 4, like 100.
Just let it sit for 72 hours.
Yes, absolutely.
Okay.
And then by the time you are focusing your intellectual effort on model number 1, maybe model number 22 will be ready.
Mm-hmm.
Maybe not, but it doesn't hurt.
It could. That's the moral of the story that I took. So then this is the last model I'm going to show. So this is the iodine-based perovskite quantum dot, where you have iodines on the anions instead of bromides. And then conveniently, a collaborator dropped this off into NERSC a couple weeks ago, so I didn't have to do much. Well, he didn't take too much care to the geometry optimization. He just ran on computationally heavy jobs like molecular dynamics. So I was just checking to see what the orbital structures were like and what the electronic structures were like. So as you can see with the dose, we do see a quantization effect here where we have...
Or maybe it is a surface state.
Or
without orbitals, we cannot say it.
Yeah, true. But usually, I mean, this is a pretty big offset though. It's like 0.4 eV.
It's too much for quantization.
Too much.
Because traps can be in the middle of the gap. Quantization is like small fractions of electron volt. So it's very likely a trap. But we do not know for sure, but it's a suspicion.
Mm-hmm. So that's the density states. And I labeled, I guess I'll go to it now. I labeled those as the like dark orbitals that don't participate in the absorption spectrum, because you can see that these orbitals from the outcar 970 and 971. And then we can see from the oscillator strengths that 690, which would be the valence band edge here, are the highest oscillator strengths. So that's why I call it dark states. So it's the first valence states that contribute to the absorption spectrum, which is plotted here. And then going forward, just to clear things up, ideally we'd like to shift this peak of the absorption spectrum closer to the HOMO-LUMO gap. So then that way we can get high photoluminescence yield from the quantum dots.
Or with this specific configuration of surface, we may just prove statement that this dot will not luminesce. Right? So if the HOMO-LUMO transition never gives substantial oscillator strengths, it means that it will be dark dot. You excite it, it absorbs, but then all photons dissolve into heat rather than emitting.
Yep.
So on experiment and on calculations, you cannot enforce each system to be bright and luminescent. There is a bit of tricks how to improve and optimized, but some of them are by their nature are dark.
Okay, so it's not necessarily.
Therefore, it is not engineering, but what we do has a little flavor of science, because we go into unknown areas and we do not have exact recipe how to make anything, like how to make this luminesce. So some materials we are identifying ability of materials to luminesce, and most of materials are dark.
That makes, so even if it does have the correct orbital structure for HOMO-LUMO, they might not necessarily.
No. It may be for this set of ligands, it will never have the right confined structure for
Just due
this.
to surface.
Sometimes yes.
Okay.
Sometimes it is energetically favorable to have localized charge on the surface, and then it is a signature of dark material. Let me serve as a broker to establish. I suggest that you guys, Aaron and John, may establish a fair trade agreement between you two, a friendly trade. So you may ask John for some education and sharing codes that he wrote, and offer him co-authorship, paying back, like being like second author in whatever you do is. So John is a owner and author of the code that allows extremely quick and efficient computation of photoluminescence, avoiding any MATLAB, or almost doing it right away from the couplings. I just do not have time to disclose, and it's he's the author, so you can communicate and next time present more results based on the calculations that are by now at your disposal from electronic structure. It's very simple script. You may talk in person and find out if you find this as a productive schedule.
I do like avoiding MATLAB whenever I can. So, yeah, I guess I don't have anything more to say, so we'll just end it there.
Okay, let's thank Aaron. Any questions? John has some.
Yeah, I do have one question. So when you're changing the scaling factors and looking at the total energies for these systems, I'm just curious, when you went from 1 to 0.9, was there any specific bond distance that happened to, like the average, like peak width would shrink towards like, the actual minimum? Like, could you contribute subtraction of specific elements to the decrease in total energy?
I caught part of it.
Please repeat the question.
Yeah, please repeat the question. I can.
Yeah.
I think we
Okay.
have the volume cranked up as high as that.
So hopefully this is a little bit better. So is there a specific bond shortening between two elements that you think contributes most or more to the lowering of total energy when you do this scaling factor test?
Well, I'd assume it'd be the lead bromide ones, because those are predominantly the band edge like orbitals. So I'd assume that those would have the biggest impact on the electronic structure that we're looking for.
Okay. Do you think by confining these materials, you're decreasing the volume of the cavity that the cesium sits in? Do you think that has any impact on the total energy? I mean, I'm just curious. That's just a couple thoughts I had.
I mean, if they're totally centered, probably not, because every charge, like all the bromides and leads, would experience the same charge. But if they're off by a little bit, you'd expect, like, if you squeezed it, like it's gonna, a 1 over r squared force, right? So as you squeeze it, some are gonna feel more force, so it might push it back. But I guess I don't think these were squeezed hard enough for that to be impacted, because like usually bond lengths are what, in between 2.7 and 3.1 for optimization. So I think the 0.9s, they were like 2.8. So I wouldn't expect the cesium or the charges of the cesium to play a huge role.
Okay.
So maybe I have just from the top of the head I thought that maybe if we replace cesium to rubidium or potassium and keep it centered and do single point, the results will be the same. But if you let it optimize, lighter atoms have smaller volume, and then the geometry will be distorted and corrugated. So it's not the interatomic distance, it's more for neutral filler to keep the shape.
Internal pressure.
Yeah.
Almost.
Yep.
Okay, thank you.
More questions to Aaron? More questions 1? More questions 2? More questions 3? Let's thank Aaron once again. So let's meet next time, next week, same place, same time. John, would you be interested to present on polyoxide titanates?
Yes.
I know that you have very interesting work on nuclear reorganization in writing too, but if you care about my opinion, I'm more interested about polyoxide titanates to send them out as quick as possible. Those are time sensitive, while nuclear reorganization is a thermal problem. You can publish it 30 years before, 30 years after, it still will be interesting.
Okay.
I'm teaching a quantum for undergraduates, and it is accompanied by MATLAB sessions on Wednesday evenings from 5 to 7 in QBB 122. So all of you here in this room are probably very well skilled in MATLAB, but if you want to have fun, you may join. It just mentioning an opportunity. And I do have an invitation from physics department. They kind of gave a voucher for our group. They asked if I want to speak, and I thought, I'm not sure, I better nominate some of the group members. And if someone is really want to speak for an hour in presence of highly critical audience, you can self-nominate. But if you don't, I nominate you. So you may squeeze together best you have and prepare. It will be like in a month or maybe 2 months from now on, Monday 3 p.m. And then all of us can come and support. John was speaking at such seminar, and he can share his experience in private, how nice or how aggressive the questions are. So the audience there is more. So first, they are not chemists; they physics people, and second, they are interested more in method development. So they will not be impressed by a range of applications. They will be more interested, like in approximations or equations, for at least like half of the talk. I know it is hard, but then it will be a really good line in your CV. Like, this can be counted as an invited talk. Invited University 7. Okay, many thanks to all of you. I think we can close the formal part of the meeting. Meeting is dismissed. And I'll stay here just in case any of us want to talk one by one. Or
So next week you want me to have a GRFP proposal as well, is that correct?
you can, but it's not practical. Maybe in 2 weeks. Next week you will give a favor by presenting on.
PT's doing?
Yes.
Okay, sounds good.
And I have asked another group member to prepare on the same paper, but then it will be clash. 2 opinions about same paper. So you, maybe we can even make a, how you call it, lawsuit. One will be attorney, another is persecutor. So you better take the role of persecutor. It is simpler.
Point out the flaws.
Yeah. John, do we need to talk?
I was just going to ask you, so this NDSU,
Please louder.
sorry. I was just going to ask a question about the NDSU KU that you mentioned in your email.
NDSU
Kansas, or
conference.
whatever. Yes.
I'm not insisting, but strongly recommend. If you're
Okay.
interested to come here, it is a good reason.
Okay.
And if you care about travel expenses, you can find ways to put them onto university budget.
Okay. And that is October 12th. 13th.
It's October 12th and 13th. But we need an abstract to reserve a spot in the schedule.
Okay.
Okay, so you will come. When will you come next week? If you will.
I would probably plan kind of the same trip I did last time. I'll probably leave Monday after lunch and try to be up there maybe sometime late afternoon or supper time on Monday, and then stay through Tuesday.
Okay.
And leave afterwards or leave Wednesday morning.
Very good. Very good. Yeah. Thank you. Anything else to discuss?
Not off the top of my head. There's a couple of other things, but I can send you an email.
Okay,
with
yeah,
those.
if you recall something, we can exchange by email or make a Skype call. Okay, then see you again, and I will disconnect the system. Turn off this
Okay, sounds good. See you then.
conference. Okay, yeah. See you.
Do we have anything?
Huh?
Do you have anything you think of off the top?